Well, so welcome to this new lecture. This is lecture number 3 on interference. And in the last lecture, we had seen Young's double slit experiment, YDSE. Let us recall what we had seen in this Young double slit experiment. I guess we had made a note on this Young's double slit experiment, and we will go through that note once again. I hope you can see this note. Young's double slit experiment. It can only happen when the sources are coherent and they have a constant phase difference between them. The sources, the two slits must be having light of the same frequency. The waves must be traveling in the same direction. Amplitudes must be nearly equal. Path difference at any point at a distance x from the center is x small d by capital D. For constructive interference, if you remember, this path difference should be equal to n lambda. For destructive interference, it should be 2n minus 1 lambda by 2. At the center, we have a bright fringe, which is known as central bright, then first dark, then first bright, then second dark, then second bright, and so on. Distance between any two consecutive bright or any two consecutive dark fringes is known as your fringe width, given by the formula of capital D lambda by small d, where capital D is the distance between the slit and the screen, and small d is the distance between the two slits. Now, we had also seen one special case where this entire apparatus is dipped in some other liquid whose refractive index is mu. We'd also seen some examples of that. If YDSE is conducted in another medium whose refractive index is mu, then speed of the wave changes, frequency of the wave remains same, and therefore the wavelength of the wave becomes lambda by mu. Therefore, since fringe width is directly proportional to lambda, the fringe width becomes beta, the original fringe width, divided by mu. Do we all understand this? Can I have some raise hand that we understand this? Right. That was about Young's double slit experiment. We had done some questions as well. Now, what remains to be done in this class is to see some more different variations of the same experiment, and that is what we will do. So I'll just put that screen on your, I'll just put that screen on. The first thing that we will do is this. What happens when a glass plate is inserted in front of any one slit? So that is the heading you will write. What is the heading you will write? When a glass slab or a glass plate is inserted in front of any slit, you have two slits. If you insert a glass plate in front of any of the slits, what happens? What we will do is, first of all, we will I will show you the diagram. It is given in your sheet only, and then we will try to understand what is happening. I think the diagram is on your screen right now. I hope you can see this diagram. Can you see this diagram on your screen? Okay, now see, what do you see in this diagram? The original experiment, you have slit S1, you have slit S2. Nothing changes here. The distance between the two slits is small d. Capital D is the distance between the slit and the screen. Now, what I have done here is we have inserted a glass slab. This glass slab has a refractive index of mu and a thickness of T. Now this glass slab is inserted in front of slit S1, upper slit. This glass slab is inserted in front of the upper slit. Now, when this glass slab is inserted in front of the upper slit, do you see this central bright fringe? This was the original central bright fringe. Do we see this? The central bright fringe, the original center bright fringe happens at the center O. Do we see this? Can I have some raise hand that we see this? The original central bright fringe was at the center O. Because of putting this glass slab, what has happened is this central fringe and all the other fringes, whether it is the first dark or first bright or central dark or second bright, all the fringes get shifted by a distance x. If I insert the slab in front of the upper slit, it will shift in the upper direction. If I insert the slab in the lower slit, it will shift in the lower direction. Do we understand this? Remember what I have said. If the slit is inserted in front of the upper slit, it will shift upwards. If the slab is inserted in front of the lower slit, it will shift in the downward direction. This x is what we need to calculate. We need to remember the formula for this x. What you got to do is you got to draw this diagram, the original diagram and this diagram. What is the difference? Here we have a glass slab of refractive index mu and thickness T. In front of the upper slit, the entire fringe pattern shifts. I will give you a minute to draw this. Okay, then we proceed. What have we seen is if we put a glass slab in front of a slit, what happens? And as I told you, we have to find out the value of this x. Now, how this value of x is achieved, let us not get into that. We can straight away write the formula, and the formula comes on your screen right now. What is the value of this x? The distance, the fringes have shifted. So this is the formula that you should remember. D by capital D by small d into mu minus 1 times d. This is the distance it has shifted. If I put the slab in front of the upper slit, it will shift in the upper direction. If I put the slab in front of the lower slit, it will shift in the lower direction. This is in terms of, this formula number 1 is in terms of capital D and small d. Remember, capital D by small d can be written as beta fringe width divided by lambda. So instead of capital D by small d, you can write this formula. You can write this formula in terms of beta and lambda. Beta is the fringe width. Lambda is the wavelength of the light which is used. So formula number 1 and formula number 2 is the formula for shifting of images. Do we understand this? Do we understand this? Okay, please note down this formula, then I will move ahead. Okay. Now there can be different things that can be asked here. We have seen how much the fringes have shifted. Now the fringe shift in the region where they were original fringes. So they can also ask by how much number of fringes the shifting has taken place. So the number of fringes by which shifting has taken place will be x divided by beta, where beta is the fringe width. X is the distance through which the fringe has shifted. If you divide it by the fringe width, you will get how many numbers of fringes have been shifted. Do we understand this? To find out how many numbers of fringes have shifted, we divide x by beta. When you divide x by beta, this is what you get. This is the number of fringes that has been shifted. So please note it down. Number of fringes that have shifted. Now, if I take a very special case, and what is this very special case? Now, remember, this is my slit S1. This is my slit S2. I put one slab here and I put one slab here. Both have the thickness T. This one has a refractive index mu1. This one has a refractive index mu2. So now I put slits. Now I put slabs in front of both the slits. In front of upper slit, I put mu1 and T. In front of lower slit, I put mu2 and T. Now remember that because of the upper slit, because of the upper slab, it will shift upwards. Because of the lower slab, it will shift downwards. I hope you understand this. Because of the upper slab, it will shift upwards. Because of lower slab, it will shift downwards. Effectively, the total shift will be given by this formula, beta by lambda into mu1 minus mu2t, or you can write it as d by small d into mu1 minus mu2t. Do we understand this? If mu1 is greater than mu2, it will shift upwards. If mu2 is greater than mu1, it will shift downwards. Do we understand this? So this is the case where both the slits have slabs in front of them. In front of the first slit, we have a slab of thickness T, refractive index mu1. In front of the slit 2, we have a slab of thickness T and refractive index mu2. The total shift is capital D by small d, mu1 minus mu2t. If mu1 is greater than mu2, it shifts upwards. If mu2 is greater than mu1, it shifts downwards. I will give you a minute to note everything down. Please note it. Let us recollect what we have seen. Number one, the first point, if I put one slit in front of the upper, if I put one slab in front of the upper slit, the pattern shifts. The pattern shifts by a distance d. This distance x is mu minus 1 times t multiplied by capital D by small d, or I can write it as beta by lambda mu minus 1 times t. That is the first formula you must remember. Then you must remember how many number of fringes have been shifted. To find the number of fringes being shifted, we divide x by beta and the answer will be mu minus 1 times t divided by lambda. If I put slabs in front of both the slits, by how much it will shift? So the formula is x will be equal to d by small d into mu1 minus mu2 times t. Here the slits have same thickness but different refractive index. You can also write it as beta by lambda into mu1 minus mu2 times t. Now you must remember whether it will shift upwards or downwards. If mu1 is greater than mu2, it will shift upwards. If you remember this, you will understand that if mu2 is greater than mu1, it will shift downwards. All of us understand this, yes or no? I'll give you time to note this down again at one place. Let us now start with a few questions that can help us in understanding the concept correctly. And let us start with this one. Let us start with this one. And this question comes on your screen right now. In Young's double slit experiment, the gap between the two slits is small d. Distance of the screen from the slits is capital D. What are the number of fringes per meter that will appear on the screen? The wavelength of the light is lambda. Can you give me the answer to this one? Anyone? What they're asking is how many fringes I will have in 1 meter. Can you apply some common sense and tell me what would be the answer for this one? A, B, C, D, 1, 2, 3, 4. What would be the answer? Yes, anyone with an answer? Number of fringes per meter. This is question number 20. What is the answer for this one? And the answer is definitely 2. Do we understand this? So basically, fringe width is lambda capital D by small d. They are not asking you what is the width of the fringe. They're asking us how many fringes I will have in 1 meter. So this is one point that you should remember. To find out how many fringes we are having in 1 meter, you will have to do what? You will have to find the inverse of the fringe width. Do we understand this? Yes or no? No, yes. Do we understand this? Okay. Let us move ahead. And see the next question solved by Prism. Then I will do this one. Let's see who gives me the answer for this one. The question comes right away. Fringe width is equal to 1 mm is observed in the interference pattern of a biprism experiment. Okay, this is for biprism. So I don't think we can do it right now. Once we are done with the biprism thing, then we will be able to do this. So let us leave it and let me do this one first. Okay, this one. In Young's double slit experiment, the interference bright fringes, you have different white fringes. You have central bright fringe, first bright, second bright, third bright, and so on. In Young's double slit experiment, the interference bright fringes are, there are 4 options given. Can you tell me which is the correct option? A, B, C, D. Can you tell me which one is the correct option here? Waiting for your answers. Are they of equal width and unequal intensities? Are they of unequal width and equal intensities? Equal width, equal intensities, or what? I'm waiting for your answers. A, B, C, D, 1, 2, 3, 4. And the correct answer is I can't see your fingers because my iPad is not working. A, B, C, D, 1, 2, 3, 4. Question number 43. And the answer is pretty simple. And the answer is equal widths and equal intensities. Do we understand this? Do we understand this? Yes or no? No or yes? Great. I'm expecting a question on this in this year's exam, and that is why I'm giving so many of doing so many of questions and spending so much of time on this, because I know that this question is going to come. Next one is this. Young's double slit experiment. If the width, that means we have two slits, very small slits. If you increase the width of that slits, remember they have not increased the distance between the slits. They have only increased the width of the slits. What will happen? The interference fringes will remain unchanged. Form is not from, it's form closer, or they will form farther away, or they will gradually disappear. So I am going to increase the width of the slits. You can use your common sense and tell me what will happen to the interference pattern. Waiting for your answers. So that slit is very, very small. If I keep on increasing the size of that slit, what will happen? And what is your answer? The answer is definitely number 4. They will gradually disappear. Yes or no? No or yes? Do you understand this? Okay. Here comes the next one, and I wanted you to note this point down, but instead of putting it in the form of a point, I put it in the form of a question. And the question goes like this. In Young's double slit experiment, monochromatic light through a single slit is eliminating S1 and S2. Interference patterns are obtained on a screen using S1 and S2. The fringe width is found to be W. Now, a sheet of mica whose thickness is T and refractive index is mu is placed in front of one of the slits. They have not told us whether it's the upper one or the lower one. Doesn't matter. What is the value of the new fringe width? They are calling the value of the new fringe width as W dash. Now they're asking us, what is the relation between W dash and W? And there are 4 options given to you, A, B, C, D. We have seen that when you insert slit, why do I say slit? When you insert a slab, the interference pattern shifts. That is a different question. Here they're asking us, what happens to the fringe width? What happens to the fringe width? And I'll give you a minute to think about it and give me the answer. Yes, bacha. What do you think is the answer? A, B, C, D, 1, 2, 3, 4. And I can definitely see 4. 4. That means the fringe width remains constant, and that is a very important point that you must remember. Fringes shift, yes, but the fringe width remains constant because all the fringes are shifted by the same distance. If all the fringes are shifted by the same distance, the fringe width will remain constant. Do we understand this? Can I have reasons from everyone? Well done. We are doing exceptionally well in this particular topic, and I am really glad that we are doing so good. What I'm going to do is take some questions from your previous exams as well, so that we can. Okay, here is a question from Ames, and let us see who is going to clear Ames this time. And see, this is how questions are framed, and this is what we have already studied. So this question goes like this. Young diversity respective monochromatic light is used to eliminate two slits A and B. Interference fringes are observed on a screen placed in front of the slates. Now, if a thin glass plate is placed normally in the path of the beam coming from one of the slates, what happens? A, B, C, D. Question number 2 is what we are asking. Question number 2 is what we are asking, and I am waiting for your answers. And what is the answer? Here, I've placed the slit. Why do I say slit? I placed a slab in front of a slit. What happens? And the answer is, I've already done this question just now. And the answer is number 4. There will not be any change in the fringe width. Fringe width remains constant. Do we understand this? Yes or no? No or yes? Again, one of the questions, just to give you a revision of, it can be asked in different ways. What is the part difference for destructive interference? N lambda, n into 1 plus lambda, n plus 1 by 2 lambda, or 2n plus 1 lambda by 2. What is the answer now? What is the answer now? And the answer is number 4. We have seen the formula as 2n minus 1 lambda. Remember, beta, you write it as 2n minus 1 lambda by 2, or you write it as 2n plus lambda by 2. Please remember this. You write it like this, or you write it plus, doesn't matter. The only thing is, in this formula, n starts from 1, and in this formula, n starts from 0. I prefer the first formula, because to get the value of first dark fringe, I will put the value of n as 1. But in the formula that is given now, to get first dark fringe, I will have to put the value of n as 0. Do we understand this? The formula that I gave you, 2n minus 1, to get the value of first dark fringe, you have to put the value of n as 1. The formula that they have given, to find out the position of first dark fringe, you have to put n ka value as 0. That is the difference between the two things. I'll leave it to you to decide which formula you want to use. Let us okay, before going any further, let me finish the other part that is remaining, so that we can solve all of the questions together. And this is the next thing that is remaining. Again, you just see what is happening here and just remember the formula here. It is difficult for you to understand it probably, and I understand this. You just have to remember the formula, write the heading, and remember the formula. Also, if you can remember the diagram, it is good. This is known as Renal Biprism. We encountered a question of Renal Biprism, and I've seen a few questions that has come for Renal Biprism. Now, what happens here? In the first case of young double slit experiment, how did we create coherent source? We had a single source, and then we put a cardboard and we put in two slits, and that is how we had created two sources from a single source. Do we understand this? Yes or no? No or yes? We had used division of wavefronts. The wavefronts had been divided. Yes or no? No or yes? Now, Fresnel biprism, we can again produce two coherent sources from a single source. Do you see this single source here? S. This S is your single source. Give me high five that we see this single source, sir. And we put a prism in front of this. The prism angle is alpha. We put a prism in front of it. Because of reflection from the prism, we will have two sources, S1 and S2, separated by a distance d. This is how Fresnel biprism converts a single source into two sources. Do we understand this? What you need to remember in this formula, in this diagram, is the prism angle is alpha. The distance of the prism from the slit is A. Distance of the screen from the prism is B. Total distance is capital D. And the distance between the two sources is given by this formula. So please draw this diagram and mark these things. What are the things that you mark? Distance between the two sources is 2 times A into mu minus 1 alpha, where A is the distance of the prism, alpha is the angle of the prism. Then the total distance becomes A plus B. B is the distance of the prism from the screen. The fringe width is same, D times lambda by small d, but the value of small d here is given by this formula. Do we understand this? So I'll give you 2 minutes, 3 minutes to draw this diagram. You only need to draw this diagram to understand from where what thing has come. That's all. I'll give you 2 minutes to draw it. Okay, so you see that we produce two sources from a single source. Remember, the formula for beta remains same. It is d times lambda by small d. Here the value of capital D is A plus B. You have already noted it down. The value of small d is 2A into mu minus 1 times alpha. Remember, A is the distance of the prism from the slit. Mu is the refractive index of the prism, and alpha is the angle of the prism. When I put this in the original formula, this is how the original formula looks like. Instead of capital D, we have A plus B. In place of small d, we have 2A into mu minus 1 times alpha. Do we understand this? The formula looks a bit complicated, but if you remember the value of capital D and small d, the formula becomes very, very small. Can you note down this formula for me? I'll give you a minute. Note it down. I will wait. Then there is one small thing that you must remember. I showed you an angle delta there. This angle delta, you can remember this formula. This tan of this angle delta, I have written alpha. Tan of this angle delta is equal to d by 2a, or you can write this angle delta, if angle is very small, as d by 2a. Sometimes this delta is given to you. What is this delta? You can see it in the original diagram, and I will show you it from the original diagram. I hope you have noted down this delta from the original diagram. From the original diagram, do you see this delta here? Do you see this delta here? Yes or no? No or yes? This is that delta, and the value of this delta is d by 2a, or tan of this delta is d by 2a. This is one very important information that you must note down. I will give you a minute for you to note it down. Let me move ahead and solve some problems. This is the first problem that we encounter. In a biprism experiment, that is the Fresnel biprism experiment, coherent sources are obtained by which of the following phenomena? Refraction, reflection, interference, and diffraction. Remember, in a Fresnel biprism, we have one source. We have one source, and with that one source, we are creating two virtual sources. By what phenomena are we creating those two virtual sources? Refraction, reflection, interference, diffraction. And your answer is, remember, in YDSE, original YDSE, it was because of the phenomena of diffraction we were creating. What about here? Can I have your answers, please? And the answer is 1. Yes. We are using a prism. A prism refracts. It does not reflect. So the answer is A. Do we understand this? Everyone in the class, please raise your hands. Great going this. I must congratulate you. But then comes the next one. And let me see whether you have understood this or not. In Phenyl biprism, coherent sources are obtained by, again, I told you there are two ways to obtain coherent sources: division of wavefront, division of amplitude. And the options are right in front of your eyes. Division of wavefront, division of amplitude, division of wavelength, none of the above. Question number 27 is what we are talking about. And the answer is number 1, division of wavefront. Whether it is original Young double slit experiment or this one, it is by the phenomena of division of wavefront. I give you an example of division of amplitude, that is known as interference by thin films. That is where amplitude divides. Amplitude only divides when we see interference pattern between reflected rays or refracted rays, then only we have division of amplitude. Do we understand this? Well, Fresnel biprism. The next one comes, and let me see whether you understand this or not. Question number 28. In Fresnel biprism experiment, the two coherent sources are real, imaginary. One is real, other is imaginary. None of the above. We've seen the Fresnel biprism experiment. And remember that there was one real source, S. Because of refraction, it creates two. But those two are not real. They are definitely imaginary. And therefore, the two sources are imaginary. Remember, the distance between the two sources is 2a into mu minus 1 times alpha. Don't forget it. Don't forget it. Fresnel biprism. If the paper is tough, then you can expect a question from Fresnel biprism experiment. I have more lined up for you. This is the next one. Information-based question. In Fresnel biprism experiment, which of the following light sources are used to locate central bright fringe? What you need to locate the central biprism? This is an information-based question. The answer to this one is white light. So remember this. This is an information-based question. White light is used to determine or to locate the position of the central fringe. Can you remember this? Okay. Then comes the next question, which I'm sure you would be able to answer. In Phenyl biprism, separation between the slits is halved, and the distance between the screen and the slit is doubled. And the question is not there. What happens to the fringe width? So I will just put the question, what happens to the fringe width, beta? It will remain unchanged, it will be half, it will be double, it will be 4 times. Infernal biprism. The distance between the screen and slit is doubled. And the distance between the slit is halved, it will become 4 times. Do we understand this? Yes or no? No, yes. Well done. Good going. Okay, then. I think we are done with almost all the questions that were possible here in this particular topic. Well, what we have done in this topic on interference, we had seen the phenomena of superposition. Whenever two waves are traveling in the same medium, they will overlap. At some points, you will have overlap. To find out the displacement of that point, you add the two wavelengths and you get a new wave. If those waves are traveling in the same direction, having the same or equal amplitudes, almost the same frequency, then this phenomena is known as interference. At some point, you will have constructive interference. At some point, you will have destructive interference. We are done with interference. I'll give you time to now go through those notes and ask me any doubts. I will wind up today's class here because there is no light here at my place and my computer is going to shut down very soon. So I finished this topic on interference. We'll meet in the next class. If you have any doubts, you can ask me there. In the next class, we'll be starting with the next topic. We had heard about diffraction and polarization. We'll start with diffraction and polarization. See you in the next class. Take care and have a nice day. If you have any doubt, please let me answer them. Take care. Bye bye.